You are made of atoms. Every breath you take, every thought that crosses your mind, every cell in your body consists of atoms assembled in intricate patterns. But where did these atoms come from? The answer is more astounding than you might imagine. Atoms were not always here. There was a time when the universe contained no atoms at all. No hydrogen, no oxygen, no carbon. Nothing that could form molecules, build stars, or create life. Just raw energy churning in a cosmic furnace so hot that atoms could not exist. Think about that for a moment. The universe had a beginning, and at that beginning, there were no atoms. The building blocks of reality as we experience it simply did not exist yet. There were no chemical reactions because there was no chemistry. There were no solid objects because there were no elements to build them from. There was no water, no rock, no metal, no organic compounds. The periodic table that hangs on the wall of every chemistry classroom, that testament to nature's organizational genius, was completely empty. Every single box, from hydrogen at position 1 to uranium at position 92, represented something that did not yet exist in the universe. This raises a profound question that has haunted humanity since we first began contemplating our origins. How do you get something from nothing? How does a universe devoid of atoms transform into one teeming with them? How does nothingness give birth to hydrogen, helium, carbon, oxygen, and all the rest? The answer involves some of the most extreme physics imaginable, conditions so bizarre and violent that they strain human comprehension. This is the story of how everything came from nothing. It is a journey that begins in a realm where physics itself barely makes sense, where quantum mechanics allows particles to spontaneously appear and disappear, where the rules we take for granted simply do not apply. We will witness the universe's first fraction of a second, when temperatures reached levels we can barely comprehend. We will watch as quarks condensed from pure energy, then bound together into the first protons and neutrons. We will see these particles fuse in the universe's primordial nuclear furnace, creating the lightest atomic nuclei. And we will fast forward through hundreds of thousands of years to the moment when electrons finally captured these nuclei, forming the first true atoms. But the story does not end there. Those primordial atoms were only hydrogen, helium, and traces of lithium. Every other element in the periodic table, from the carbon in your DNA to the iron in your blood, from the calcium in your bones to the gold in jewelry, had to be forged somewhere else. That somewhere was inside stars, those brilliant nuclear reactors scattered across the cosmos, and for the heaviest elements not even stars suffice. Those required the most violent explosions in nature, events so energetic they briefly outshine entire galaxies. The journey we're about to take spans more than 13 billion years of cosmic history. It encompasses scales from the smallest distances physics can measure to structures larger than galaxy clusters. It involves temperatures from nearly absolute zero to trillions upon trillions of degrees. And remarkably, improbably, wonderfully, this process that began with quantum foam and ended with conscious beings asking questions about their own origins can be understood. We can trace the lineage of every atom in your body back to its creation, whether that happened in the first minutes after the Big Bang or in the death throes of a massive star billions of years later. If you are ready to understand the origin of everything you see and touch, hit that like button and subscribe. We are about to dive deep into one of physics' most profound questions. Prepare yourselves. We begin at the very edge of existence itself. To understand how atoms formed from nothing, we must first redefine what nothing means. In everyday language, nothing is the absence of everything. Empty space, a void, darkness and silence extending infinitely in all directions, containing not a single particle, not a whisper of energy, not even the potential for anything to exist. This intuitive definition of nothingness seems straightforward enough. Remove all matter, remove all radiation, remove everything, and you are left with nothing. But physics tells a radically different story. In the quantum realm, absolute nothingness cannot exist. This counterintuitive truth challenges our deepest intuitions about reality and forces us to reconsider the very meaning of existence. The quantum vacuum, what we might naively call empty space, turns out to be anything but empty. It seethes with activity, a roiling sea of energy and virtual particles that pop in and out of existence so rapidly we cannot directly observe them. Yet their effects are real and measurable. This counterintuitive truth arises from one of the most fundamental principles in physics, formulated by Werner Heisenberg in 1927. The uncertainty principle states that certain pairs of properties, called conjugate variables, cannot be precisely known simultaneously. The more accurately you measure a particle's position, the less accurately you can know its momentum, and vice versa. This is not a limitation of our measuring instruments or our experimental techniques. It is a fundamental feature of reality itself, baked into the mathematical structure of quantum mechanics. Heisenberg's insight revolutionized physics because it revealed that the universe is inherently probabilistic at its most fundamental level. In classical physics, you could theoretically know everything about a system. Given perfect information about the position and momentum of every particle, you could predict the future with absolute certainty. Quantum mechanics shattered this deterministic worldview. There are limits to what can be known, not because of ignorance, but because certain properties simply do not have definite values until they are measured. But there is another version of this principle that becomes crucial for understanding the universe's origin. Energy and time form another pair bound by uncertainty. This relationship can be expressed mathematically, but the essence is simple. Over short enough time intervals, the energy content of any region of space can fluctuate wildly. The more precisely you try to specify the time interval, the more uncertain the energy becomes. And this uncertainty is not small. It can be enormous. This relationship, expressed mathematically as the uncertainty in energy multiplied by the uncertainty in time, must be at least a certain minimum value, has staggering implications. It means that over short enough time intervals, the energy content of space can fluctuate wildly. Particles can spontaneously appear out of what seems like emptiness, borrowing energy from the vacuum itself. These are called virtual particles, and they appear and disappear constantly throughout the universe, even in the most perfect vacuum you could create. They emerge in pairs, a particle and its antiparticle, exist for a fleeting instant determined by how much energy they borrowed, then annihilate each other and vanish back into the void. The name virtual particles might suggest they are not real, merely mathematical conveniences or bookkeeping devices in calculations, but their effects are measurable and have been confirmed in countless experiments. The Casimir effect, for instance, occurs when two uncharged metal plates are placed very close together in a vacuum. Theory predicts, and experiment confirms, that these plates experience an attractive force, pushing them together. This force arises because virtual particles with wavelengths longer than the gap between the plates cannot exist in that gap, while virtual particles of all wavelengths can exist outside. This creates an imbalance in vacuum energy that manifests as a physical force. Similarly, the Lamb shift, a tiny difference in energy levels of the hydrogen atom, arises from the interaction between the electron and virtual photons constantly appearing and disappearing in the electromagnetic field around the nucleus. These and other phenomena prove that virtual particles, while ephemeral and not directly observable, are as real as any other aspect of quantum physics. The vacuum is not empty. It is a dynamic medium, constantly fluctuating with quantum activity. Under normal circumstances, these quantum fluctuations remain inconsequential curiosities. They have measurable effects in precision experiments, contributing to phenomena like the Casimir force and the Lamb shift, but they do not create permanent matter. The particles appear and disappear too quickly to interact significantly with anything. Virtual particles exist for such infinitesimally short times that they cannot travel far or participate in complex interactions. They are, in essence, quantum noise, background static in the fabric of space-time, but conditions in the universe were not always normal. In the very first moments after the Big Bang, something extraordinary occurred that transformed these ephemeral quantum ghosts into the foundation of all reality. The key lies in something physicists call the false vacuum. To understand this concept, imagine a ball sitting in a shallow depression on a hillside. The ball is in a stable position, settled in a local minimum of energy. It could sit there indefinitely. But it is not in the lowest possible energy state. There is a deeper valley farther down the slope. If given enough energy to overcome the rim of the depression, the ball would roll down to that much lower valley, releasing potential energy as it goes. The false vacuum is similar. It is a state of space that seems stable, but actually contains tremendous potential energy waiting to be released. It is like water that has been supercooled below its freezing point but has not yet crystallized into ice. It is in a metastable state, temporarily stable, but ready to transition to a lower energy configuration if given the right trigger. According to inflationary theory, developed primarily by physicists Alan Guth, Andre Linde and Paul Steinhardt in the early 1980s, the universe began in such a false vacuum state. The story of inflation's discovery is itself fascinating. In the late 1970s, cosmologists recognized that the standard Big Bang model, while successful in many ways, had several serious problems. The horizon problem asked why distant regions of the universe that seem like they should never have been in causal contact have the same temperature to extraordinary precision. The flatness problem questioned why the universe appears to have exactly the critical density needed to be geometrically flat, a condition that requires incredible fine-tuning in the early universe. And the monopole problem noted that grand unified theories of particle physics predicted copious production of magnetic monopoles in the early universe, yet we observe none. Alan Guth, then a postdoctoral researcher, realized in 1979 that a period of exponential expansion in the very early universe could solve all these problems at once. If the universe underwent a brief period where it doubled in size again and again in rapid succession, it would explain why distant regions are similar, why space appears flat, and why monopoles are absent. They would be diluted to undetectable levels by the expansion. Guth called this process inflation, and although his original formulation had technical problems, it sparked a revolution in cosmology. In this false vacuum condition, space itself possessed an enormous energy density. This energy was not in the form of particles or radiation, but was inherent to the vacuum itself, a property of whatever quantum field was in this excited state. Physicists call this hypothetical field the inflaton, though its precise nature remains unknown. What matters is that this vacuum energy had a peculiar property. Unlike normal matter or radiation, whose density decreases as space expands, vacuum energy maintains a constant density. As space expands, more vacuum energy appears to fill the new space. This seemingly innocuous property has dramatic consequences when combined with Einstein's general relativity. Einstein's equations show that energy curves spacetime, and that curvature manifests as gravity. Normally, energy attracts. Mass pulls on mass. But vacuum energy behaves differently. The pressure associated with constant density vacuum energy is negative, and this negative pressure creates a repulsive gravitational effect. The vacuum pushes space to expand rather than pulling it to contract. This drove a period of exponential expansion called cosmic inflation, occurring in the first tiny fraction of a second after the universe's beginning. During inflation, which lasted somewhere around 10 to the negative 35 seconds, the universe expanded by a factor of at least 10 to the 26th. To put this in perspective, an object the size of a proton would expand to roughly the size of a grapefruit or larger. Some models suggest the expansion factor could have been far greater, perhaps 10 to the 60th or more. This expansion was not gradual, it was explosive, doubling in size again and again in intervals almost too brief to conceive. Imagine a balloon inflating, but instead of taking seconds or minutes, each doubling happens in a time interval of about 10 to the negative 37 seconds, and instead of doubling a few times, it doubles 100 times or more. The scale of this expansion is mind-boggling. A region of space smaller than a single elementary particle expanded to become larger than the observable universe today. Everything we can see, every galaxy and star and planet, all emerge from a patch of space so tiny it would be lost inside a proton. But here is where quantum fluctuations become crucial. During inflation, quantum fluctuations in the vacuum were occurring constantly, just as they do today. Particle-antiparticle pairs appeared, and normally would have disappeared. The uncertainty principle allowed these virtual particles to borrow energy from the vacuum for brief instants. In normal circumstances, they would exist for maybe 10 to the negative 23 seconds before annihilating and returning the borrowed energy. But inflation changed everything. The exponential expansion of space stretched these quantum fluctuations faster than they could reconnect and annihilate. Think about it this way. A virtual particle pair appears, separated by a tiny distance determined by the uncertainty principle. Normally, they would come back together almost instantly and annihilate. But if, in that tiny instant, space itself expands by a factor of 2, the distance between them doubles, expand again, and it doubles again. After 100 doublings, they are separated by an incomprehensibly large distance, far too large to ever find each other again. Virtual particles that would have existed for only a fraction of a second found themselves separated by vast distances as space itself expanded between them. They could not find each other again. They could not recombine. The energy debt they borrowed from the vacuum could not be repaid in the normal way. They had to become real. They transitioned from virtual to actual, from temporary to permanent. The energy debt they borrowed from the vacuum had to be paid by something else. That something was the energy driving inflation itself. The false vacuum's energy density decreased as it gave birth to real particles from quantum fluctuations. These particles, initially just fluctuations in various quantum fields, became permanent features of reality. Every particle that exists today, every quark and electron and photon, can trace its lineage back to quantum fluctuations that were stretched to macroscopic scales during inflation and made real by the universe's expansion. When inflation ended, the remaining energy in the false vacuum was released in a tremendous burst called reheating. The inflaton field, having driven the exponential expansion, finally decayed into ordinary particles. This decay was not instantaneous but happened over a brief period, perhaps lasting a tiny fraction of a second by cosmic standards. The energy that had been locked in the false vacuum state converted into a hot, dense soup of particles that would eventually cool and organize into atoms, stars, galaxies, and everything we see today. The temperature during reheating was extraordinary, perhaps reaching 10 to the 32nd power degrees Kelvin or higher. At such temperatures, particles collided with such energy that they could create any particle allowed by physics, including the heaviest particles that exist or ever existed. The universe was filled with quarks, leptons, gauge bosons, Higgs bosons, and likely particles we have not yet discovered or cannot create in our accelerators. It was a particle zoo, a dense soup where every type of matter and antimatter coexisted in thermal equilibrium. This process sounds like magic, creating something from nothing through a quantum loophole and exponential expansion. Yet it explains multiple mysterious features of our universe that would otherwise seem like impossible coincidences. It explains why the universe appears nearly flat in its geometry, meaning parallel lines remain parallel even over cosmological distances. Inflation stretched any initial curvature so thin that space looks flat even across billions of light years. It is like blowing up a balloon. The surface of a small balloon is obviously curved, but if you inflate the balloon to enormous size, any small patch of its surface appears essentially flat. The same principle applies to the universe. Whatever its initial curvature might have been, inflation expanded it so much that we perceive flatness. It explains why distant regions of the universe that seem like they should never have been in contact have the same temperature to extraordinary precision. When we measure the cosmic microwave background radiation coming from opposite directions in the sky, we find regions separated by billions of light years that have identical temperatures to within 1 part in 100,000. How did these regions know to have the same temperature if they were never in causal contact? Inflation answers this puzzle. Before inflation, these regions were in contact. They were close enough to exchange energy and equilibrate to the same temperature. Then, inflation blew them apart faster than light could travel between them. They appear causally disconnected now, but they share a common history before inflation separated them. And most remarkably, it explains where the seeds of cosmic structure came from. Those quantum fluctuations that got stretched to cosmic scales were not perfectly uniform. The quantum nature of fields means they fluctuate randomly, with some regions slightly higher in energy density and others slightly lower. These variations are governed by the statistics of quantum mechanics, producing a specific pattern of fluctuations across different scales. Some regions had slightly more energy density, others slightly less. These tiny variations, originating from subatomic quantum randomness smaller than any particle, got magnified to astronomical scales by inflation. A fluctuation that started out smaller than a proton ended up spanning millions or billions of light years. This is not metaphor or analogy. The quantum fluctuations we can measure in laboratory physics experiments, the random jitter that occurs at the smallest scales, were literally inflated to become the largest structures in the universe. When the universe cooled enough for matter to begin clumping under gravity, these variations served as the seeds. Regions with slightly more density attracted more matter, eventually forming galaxies, galaxy clusters, and the vast cosmic web of structure we observe. The quantum foam of the vacuum, amplified by inflation, became the blueprint for every star and planet that would ever exist. The galaxies we see today, including our own Milky Way, grew from quantum fluctuations that occurred in the first infinitesimal fraction of a second after the Big Bang. We can test this prediction by examining the cosmic microwave background radiation in detail. When satellites like COBE, WMAP, and Planck measured the temperature variations in the cosmic microwave background across the sky, they found a specific pattern. The pattern matches almost perfectly what inflation predicts. The fluctuations have a characteristic scale. They are Gaussian, meaning they follow a bell curve distribution. They have slightly more power on large scales than small scales, exactly as expected from quantum fluctuations in an inflating spacetime. This agreement between theory and observation is one of the most stunning successes of modern cosmology. In a very real sense, the universe did come from nothing, or at least from something as close to nothing as physics allows. Not from literal non-existence, which may be a concept that makes no sense in a quantum universe, but from a quantum vacuum in a special energetic state. The false vacuum was not filled with matter, or even with stable particles, but it had properties, governed by quantum fields that could fluctuate and change. When those fluctuations met the runaway expansion of inflation, they became real, they became permanent, they became the raw material for everything that followed. Think about the philosophical implications for a moment. The entire observable universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars with untold numbers of planets, and perhaps countless instances of life, all emerge from quantum fluctuations in a patch of space smaller than a single atom. Everything that exists, every particle, every force, every structure, traces back to quantum uncertainty in the vacuum. The foundation of reality is randomness amplified by cosmic expansion, yet this randomness was not chaotic. It followed precise mathematical laws. The quantum fields fluctuated according to the principles of quantum mechanics. The inflation proceeded according to general relativity and particle physics. The result was a universe that, while not predetermined in its details, followed predictable statistical patterns. We can calculate what kinds of fluctuations should emerge from quantum vacuum during inflation, and we find they match what we observe in the cosmic microwave background and in the distribution of galaxies. This is not the end of the story, merely the beginning. These primordial particles were not atoms. They were not even the building blocks of atoms yet. The universe was far too hot and energetic for complex structures to form. What emerged from inflation was a seething plasma of fundamental particles, all moving at nearly the speed of light, all interacting in ways we can barely recreate, even with our most powerful particle accelerators. To understand how atoms formed, we must follow this primordial plasma as it cooled and evolved, first into quarks and gluons, then into protons and neutrons, then into atomic nuclei, and finally, hundreds of thousands of years later, into the first true atoms. The journey continues, and it becomes more concrete, more tangible as we move forward in cosmic time. The quantum weirdness of the first instant gives way to the more familiar physics of hot plasmas, nuclear reactions, and atomic structure. But never forget that foundation. Everything that follows, all the nuclear physics and chemistry and biology, all the stars and planets and life, began with quantum fluctuations in a vacuum field during a period of exponential expansion that lasted less time than it takes light to cross the diameter of a proton. The universe emerged from almost nothing, and that emergence left marks we can still detect today. When inflation ended and the false vacuum decayed, it released its energy into a form physicists call reheating. The universe, having just undergone its exponential expansion, was suddenly flooded with energy that converted into particles. The temperature at this moment was incomprehensibly hot, perhaps 10 to the 32 degrees Kelvin. To put this in perspective, the core of the Sun reaches about 15 million degrees Kelvin. The early universe was more than 1,000,000 billion times hotter. At such temperatures, even the most fundamental structures of matter cannot hold together. Today, when we look at matter, we see it organized in a hierarchy. Atoms contain nuclei and electrons. Nuclei contain protons and neutrons, and protons and neutrons in turn are made of even smaller particles called quarks, held together by particles called gluons. But this structure only exists because the universe is relatively cool. In the first moments after the Big Bang, temperatures were so extreme that this hierarchy broke down completely. Quarks and gluons could not bind together. They existed as free particles in what physicists call a quark-gluon plasma. This state of matter is as exotic as it sounds. Quarks are the fundamental building blocks of protons and neutrons. They come in 6 varieties called flavors: up, down, strange, charm, bottom and top. In the early universe, all these flavors existed, though the heavier ones like top and bottom quarks were unstable and quickly decayed. The lighter quarks, particularly up and down quarks, were the survivors that would eventually form all the ordinary matter in the universe. Gluons are the force carriers of the strong nuclear force, the most powerful force in nature. They literally glue quarks together into composite particles. But at temperatures above about 2 trillion degrees Kelvin, this glue does not hold. The strong force, despite its name, becomes weaker at higher energies and shorter distances, a property called asymptotic freedom. This sounds backwards until you consider how forces actually work. Forces are transmitted by virtual particles, and at very high energies, there is so much energetic chaos that the exchange of these virtual particles becomes less effective at binding particles together. The quarks and gluons move so fast and collide so violently that they cannot settle into stable configurations. They remain free, moving independently through space. The quark-gluon plasma filled the entire universe during what is called the quark epoch, lasting from about 10 picoseconds to several microseconds after the Big Bang. 1 picosecond is 1 trillionth of a second. The fact that we can discuss events occurring on such timescales with any confidence is remarkable. We cannot directly observe the universe at these early times. Light from this era has long since been absorbed and rescattered, but we can recreate similar conditions in laboratories. Particle accelerators like the relativistic heavy ion collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN have smashed heavy nuclei together at velocities approaching the speed of light. When gold nuclei or lead nuclei collide head-on at these speeds, the hundreds of protons and neutrons in each nucleus release their kinetic energy in a tiny volume. For a fleeting instant, lasting only about 10 to the negative 23 seconds, the collision creates a tiny droplet of quark-gluon plasma. These experiments have revealed that quark-gluon plasma behaves like a nearly perfect liquid. This surprised physicists, who initially expected it to behave like a gas of weakly interacting particles. Instead, quarks and gluons in this plasma flow, together with minimal internal friction, exhibiting collective behavior despite their fundamental nature. The plasma expands rapidly, cooling as it does. Within that brief moment of existence, before it cools enough for quarks to bind into hadrons again, scientists can study its properties using the debris of particles that fly out from the collision. What these experiments have taught us is how matter transitions from this free quark state to the confined state we know today. As the universe expanded after the Big Bang, it cooled. Temperature and density dropped continuously. Somewhere around a few microseconds after the beginning, when temperatures fell below approximately 2 trillion degrees, a phase transition occurred. This was not a gradual change, but a relatively sudden shift, similar to how water suddenly freezes into ice when cooled below 0 degrees Celsius. This transition is called hadronization, or confinement. The strong force, which had been relatively weak at the extreme temperatures of the quark-gluon plasma, became dominant as the universe cooled. Gluons began successfully binding quarks into larger particles. 3 quarks would combine to form baryons, the family of particles that includes protons and neutrons. A quark and an antiquark would bind to form mesons, unstable particles that quickly decayed. The era of free quarks was over. The hadron epoch had begun. But something remarkable happened during this transition, something that made our existence possible. The universe should have contained equal amounts of matter and antimatter. Every quark should have been paired with an antiquark, every electron with a positron. As the universe cooled and particles began finding their antiparticles, they should have annihilated each other completely, leaving nothing but radiation. The fact that we exist proves this did not happen. There was an asymmetry, a tiny excess of matter over antimatter. The exact ratio was about 1 extra matter particle for every billion matter-antimatter pairs. When the annihilation occurred, obliterating the vast majority of particles in a flash of energy, this small excess remained. Every atom in your body, every star in the sky, every planet and moon and asteroid, all of it comes from this asymmetry. Where this asymmetry came from remains one of the great unsolved questions in physics. Theories propose various mechanisms, but we do not yet know for certain why the universe favoured matter slightly over antimatter. What we do know is the outcome. As hadronization completed, the universe contained mostly radiation from all the annihilated particles, plus a small fraction of surviving matter in the form of quarks bound into hadrons. The most stable of these hadrons were protons made of 2 up quarks and 1 down quark, and neutrons made of 1 up quark and 2 down quarks. These particles were not yet organized into atomic nuclei. They existed as a hot plasma of free protons and neutrons mixed with electrons, neutrinos and photons, all moving at nearly the speed of light. The universe was still far too hot for nuclei to form. Any time a proton and neutron tried to bind together, the intense radiation and high-energy collisions tore them apart again. But the temperature continued dropping. The universe continued expanding, and soon, in the cosmic scheme of things, conditions would become suitable for the next critical step: nuclear fusion on a cosmic scale. The stage was set for Big Bang nucleosynthesis, when the first atomic nuclei would forge together in the primordial furnace of the early universe. 1 second after the Big Bang, the universe had cooled to about 10 billion degrees Kelvin. This might still seem impossibly hot, but it represented a 1,000-fold drop from the peak temperatures moments earlier. At this temperature, a critical change occurred. Neutrinos, which had been interacting frequently with other particles, became too low in energy to interact effectively. They decoupled from the rest of matter and radiation, streaming freely through space. These neutrinos still exist today as a cosmic neutrino background, analogous to the cosmic microwave background but much harder to detect. More importantly for our story, at about 1 second after the Big Bang, the ratio of neutrons to protons froze out. Earlier, when temperatures were higher, neutrons and protons constantly converted into each other through weak nuclear interactions. A neutron could interact with a positron to become a proton, or a proton could interact with an electron to become a neutron. These reactions maintained an equilibrium ratio determined by the temperature and the slight mass difference between neutrons and protons. Neutrons are about 0.1% heavier than protons, and at very high temperatures, this difference is negligible. But as the universe cooled, the equilibrium shifted toward protons. By the time the universe was 1 second old, the temperature had dropped enough that these conversion reactions became too slow to maintain equilibrium. The ratio locked in at about 1 neutron for every 6 protons. However, free neutrons are unstable. They decay into protons with a half-life of about 880 seconds, or roughly 15 minutes. Over the next few minutes, some neutrons would decay, but many would be saved from this fate by binding into stable nuclei. The crucial moment for nucleosynthesis came when the universe was about 3 minutes old and had cooled to roughly 1 billion degrees. At this temperature, something remarkable became possible. Protons and neutrons could finally stick together when they collided, binding through the strong nuclear force to form deuterium nuclei. Deuterium, also known as heavy hydrogen, consists of 1 proton and 1 neutron. Today it exists as a stable but rare isotope of hydrogen. In the early universe, it became the essential stepping stone for building heavier elements. But there was a bottleneck. This bottleneck is called the deuterium bottleneck, and it delayed nucleosynthesis for those crucial first few minutes. The problem was that deuterium has a binding energy of only about 2.2 million electron volts. At temperatures above about 1 billion degrees, there were still enough high-energy photons present to break deuterium apart as soon as it formed. Imagine trying to build a house of cards in a windstorm. Every time a proton and neutron managed to bind together, a photon would smash into them and knock them apart again. As the universe expanded and cooled past this critical temperature, the deuterium bottleneck opened. Suddenly, deuterium could survive long enough to participate in further reactions, and when deuterium became stable, nuclear fusion proceeded rapidly. A deuterium nucleus could fuse with another neutron to form tritium, an isotope of hydrogen with 1 proton and 2 neutrons, or it could fuse with a proton to form helium-3, with 2 protons and 1 neutron. These isotopes could then fuse with additional deuterium nuclei or with each other. The most important product of this fusion chain was helium-4, the common isotope of helium with 2 protons and 2 neutrons. Helium-4 is extraordinarily stable, with a binding energy much higher than the light isotopes that formed it. Once neutrons and protons got locked into helium-4 nuclei, they stayed there. The process was efficient. Calculations show that almost all available neutrons ended up in helium-4. Starting with a neutron-to-proton ratio of about 1:6 after accounting for neutron decay, the fusion process incorporated these neutrons into helium, pairing each 2 neutrons with 2 protons. The mathematics of this process are straightforward and powerful. Out of every 16 nucleons, meaning protons and neutrons combined, roughly 2 neutrons and 14 protons were available after the first few minutes. These 2 neutrons combined with 2 of the protons formed one helium-4 nucleus. The remaining 12 protons stayed as hydrogen nuclei. This gives a ratio of 1 helium-4 nucleus for every 12 hydrogen nuclei. By mass, since helium-4 is 4 times heavier than a single proton, this means about 25% of the ordinary matter in the universe should be helium. This prediction, made theoretically in the 1940s and refined substantially in the decades since, matches observations almost perfectly. When astronomers measure the helium abundance in old stars, in interstellar gas clouds, in distant galaxies, they consistently find that roughly 25% of ordinary matter by mass is helium-4. This remarkable agreement between theory and observation is one of the strongest pieces of evidence supporting the Big Bang model. It would be nearly impossible to explain this universal helium abundance through stellar processes alone. Stars do create helium by fusing hydrogen in their cores, but they produce it locally and cannot account for the uniformity we observe across the entire cosmos. Big Bang nucleosynthesis did not stop at helium-4. Small amounts of other light nuclei also formed. Some deuterium survived without fusing into heavier elements, leaving the universe with a trace abundance of about 0.02% deuterium by mass. Helium-3, being relatively stable, also survived in small quantities, and through more complex reaction chains, tiny amounts of lithium-7 and beryllium-7 formed. Lithium-7 consists of 3 protons and 4 neutrons. It could form through the fusion of helium-4 and tritium, or through the fusion of helium-3 and helium-4. Beryllium-7, which has 4 protons and 3 neutrons, later decayed into lithium-7 as well. But nucleosynthesis could not proceed to heavier elements. There is a fundamental gap in nuclear stability that prevented Big Bang nucleosynthesis from building carbon or anything heavier. No stable nucleus exists with 5 nucleons. Helium-5 instantly falls apart. Similarly, no stable nucleus exists with 8 nucleons. This mass 5 and mass 8 gap acts like a brick wall. To get past helium-4 with its 4 nucleons, you need to add another nucleon, giving you 5. But that nucleus does not survive. You cannot jump directly to carbon-12, which has 12 nucleons, because that requires combining 3 helium-4 nuclei simultaneously. The probability of 3 nuclei coming together at exactly the same instant is vanishingly small. Stars eventually solve this problem through the triple alpha process, which we will discuss later. But the early universe did not have the sustained high temperatures and densities necessary for this process. Big Bang nucleosynthesis lasted only about 20 minutes. By the time the universe was 20 minutes old, it had cooled to about 300 million degrees Kelvin. At this temperature, nuclear reaction rates dropped so low that fusion effectively stopped. The window for primordial nucleosynthesis had closed. The result was a universe composed of about 75% hydrogen by mass, 25% helium-4, and trace amounts of deuterium, helium-3, and lithium-7. These proportions have been verified through countless observations, giving us confidence that we understand this era of cosmic history with remarkable precision. The relative abundances of these light elements depend sensitively on the conditions during nucleosynthesis, particularly on the ratio of baryons to photons in the universe. By comparing predicted abundances with observed abundances, cosmologists can determine fundamental properties of the universe, including the total amount of ordinary matter it contains. One intriguing puzzle remains. Lithium-7 observations in the oldest stars show abundances lower than Big Bang nucleosynthesis predicts. This discrepancy, known as the lithium problem, suggest either that something destroyed primordial lithium in these stars, or that our understanding of Big Bang nucleosynthesis needs refinement. Various solutions have been proposed, from stellar physics that depletes lithium to modifications of fundamental physics during nucleosynthesis. The question remains unresolved, a small but nagging reminder that even our most successful theories have loose ends. Despite this puzzle, Big Bang nucleosynthesis stands as one of the great triumphs of modern cosmology. From knowing the temperature, density, and expansion rate of the universe during those first 20 minutes, physicists can calculate the abundances of light elements produced. These calculations match observations with stunning accuracy. Hydrogen, helium, and lithium forged in those first minutes still make up the vast majority of these elements in the universe today. But the nuclei produced were not atoms. They were bare nuclei, positively charged, surrounded by a sea of free electrons and photons. To become atoms, these nuclei needed to capture electrons. That process would take much longer. After Big Bang nucleosynthesis ended, 20 minutes into the universe's history, a strange period began. The universe contained all the raw materials needed to form atoms. Hydrogen nuclei, which are just protons, existed in abundance. Helium nuclei with their 2 protons and 2 neutrons floated through space. Free electrons, negatively charged and eager to bind with positive charges, surrounded these nuclei everywhere. Yet atoms did not form. They could not form, because the universe remained far too hot. At temperatures of hundreds of millions of degrees, photons carried enough energy to instantly ionize any atom that managed to form. The moment an electron got captured by a nucleus, a high-energy photon would smash into it and knock it free again. This was not a rare occurrence, but a constant bombardment. The universe was filled with an incredibly dense bath of radiation. For every proton or neutron in the universe, there were about 1 billion photons. This enormous photon-to-baryon ratio meant that matter was completely overwhelmed by radiation. The universe entered what physicists call the photon epoch, or the radiation-dominated era. During this time, which lasted from about 10 seconds after the Big Bang until roughly 47,000 years later, radiation carried most of the energy density in the universe. Matter existed, but was essentially a passenger, buffeted by the intense radiation field. The universe was opaque, not in the sense of being dark, but in the sense of being fog-like. Imagine trying to see through dense clouds or thick smoke. Light cannot travel far before hitting something and scattering in a different direction. In the early universe, that something was free electrons. Photons interact very strongly with charged particles through electromagnetic force. When a photon encounters a free electron, it can scatter off the electron through a process called Thomson scattering. The electron absorbs the photon's momentum, changing its direction, and immediately emits a new photon in a random direction. This process happened constantly throughout the photon epoch. A photon could not travel far, perhaps a few meters at most, before hitting an electron and scattering. The universe was like an infinite hall of mirrors, with light bouncing endlessly off the sea of free electrons. This opacity had profound consequences. It meant that different regions of space were in thermal contact with each other, even across vast distances. Photons carried energy from hot regions to cool regions, maintaining temperature equilibrium. This is why, when we look at the cosmic microwave background today, we see the universe at the end of the photon epoch was remarkably uniform in temperature, the same to within about 1 part in 100,000 across the entire sky. That uniformity was maintained by the constant shuffling of energy through photon scattering. As the universe expanded, it cooled. This cooling was inexorable and followed a simple relationship. The temperature of radiation in an expanding universe decreases in inverse proportion to the size of the universe. Double the size, halve the temperature. Over hundreds of thousands of years, the expansion proceeded steadily. The universe grew larger. The photon's wavelength stretched with the expansion, reducing their energy. Temperature dropped from hundreds of millions of degrees to millions of degrees to hundreds of thousands of degrees. But matter's energy density was also changing, and crucially, it was changing at a different rate. The energy density of radiation falls faster than the energy density of matter as the universe expands. This is because photons lose energy, both from decreasing number density and from redshift, while matter particles only experience decreasing number density. Around 47,000 years after the Big Bang, the energy density of matter surpassed the energy density of radiation for the first time. The universe transitioned from being radiation-dominated to matter-dominated. This transition marked a turning point in cosmic history. Before it, radiation pressure smoothed out any density variations in matter. Gravity tried to pull matter together, but radiation pressure pushed it apart. After the transition, gravity gained the upper hand. Matter could begin clumping together under its own gravitational attraction. The seeds for galaxy formation, planted by quantum fluctuations during inflation, could finally start growing. But atoms still had not formed. The universe was still too hot. Temperatures remained at tens of thousands of degrees. The wait continued. The universe expanded. Space grew larger. Photons continued scattering off free electrons, maintaining thermal equilibrium. Nuclei and electrons swirled through this plasma, occasionally coming close enough to interact but never binding permanently. It was like a slow-motion dance where partners never quite managed to embrace. The cosmic clock ticked onward. 100,000 years. 200,000 years. 300,000 years. Each passing millennium, the temperature dropped a little further. The photons' energy decreased. Their ability to ionize atoms weakened. Throughout this period, the universe was utterly inhospitable to complex structures. No stars existed because stars require gravity to compress gas clouds, and gravity could not effectively compress clouds that were ionized and coupled to radiation. No planets existed because planets form from solid materials and chemical processes, which require atoms and molecules. No life existed because life requires chemistry, and chemistry requires stable atoms. The universe was a sterile soup of charged particles and radiation, unthinking and unchanging beyond its gradual expansion and cooling. But conditions were approaching a critical threshold. The temperature was falling toward 3,000 degrees Kelvin. At this temperature, photons would finally lack the energy to ionize hydrogen atoms. Electrons would be able to bind to protons permanently. The dance partners would finally embrace. This moment, when nuclei and electrons combine to form the first neutral atoms, is called recombination. It is one of the most important events in cosmic history. Everything that followed, from the first stars to the last planet, from the earliest life to the latest thought, depended on this transition. Without recombination, atoms could not form. Without atoms, nothing interesting could happen in the universe. We were about to witness the birth of complexity, the moment when the universe gained the ability to organize itself into structure. Approximately 380,000 years after the Big Bang, the universe reached a temperature of about 3,000 degrees Kelvin. This temperature seems absurdly hot by earthly standards, roughly half the temperature of the sun's surface. Yet in cosmic terms, it represented a profound cooling from the billions of degrees that characterized earlier epochs. At 3,000 degrees, something remarkable became possible. For the first time since the first few minutes after the Big Bang, electrons could bind to nuclei and stay bound. The process began with helium. Helium nuclei, with their 2 protons, have a higher binding energy for electrons than hydrogen nuclei with their single proton. This meant that helium atoms could form at slightly higher temperatures than hydrogen atoms. Around 18,000 years before full recombination, when the temperature was still somewhat above 3,000 degrees, helium nuclei began capturing electrons to form neutral helium atoms. First, they captured 1 electron to form singly ionized helium. Then, as the temperature dropped further, they captured a second electron to become fully neutral helium-4. Hydrogen took longer. A single proton has less electrical attraction than the double charge of a helium nucleus, making it harder to hold onto an electron. But as the temperature continued falling, the energy of photons dropped below the ionization energy of hydrogen, which is 13.6 electron volts. This critical threshold was crossed when the universe was about 378,000 years old. Suddenly, hydrogen atoms could form and survive. You might think this would happen instantly. All the free protons would grab the abundant free electrons, forming neutral hydrogen in a flash. But recombination was actually a more subtle process that unfolded over thousands of years. The issue was that direct recombination to the ground state, the lowest energy level of hydrogen, was highly inefficient. When an electron captured directly into the ground state, it had to release all its excess energy at once. This energy came out as a single high-energy photon with wavelength corresponding to at least 13.6 electron volts in the ultraviolet range. These high-energy photons posed a problem. The universe was still filled with neutral hydrogen atoms that had recently formed. These atoms were in their ground state, ready to absorb any photon with exactly the right energy to ionize them again. So most photons emitted when an electron fell directly to the ground state would immediately be absorbed by a neighboring hydrogen atom, ionizing it. The net effect was almost no progress toward recombination. It was like trying to fill a bucket with a hole in it. Water went in, but immediately leaked out again. Nature found a workaround through a two-step process. Electrons preferentially captured into excited states of hydrogen, energy levels above the ground state. From these excited levels, electrons could cascade down through intermediate states, emitting multiple lower energy photons. The key transition involved the 2's energy level. From the second energy level, an electron could reach the ground state through 2-photon emission, releasing 2 photons simultaneously rather than 1. Each of these photons had lower energy than the ionization energy, meaning they could not ionize neighboring hydrogen atoms. They could safely escape and contribute to the cosmic background. This mechanism, though slower than direct recombination, worked. Over a span of roughly 100,000 years, the ionization fraction of the universe dropped from nearly 100% to about 10%. This means 90% of electrons had successfully bound into neutral atoms. The process accelerated as it proceeded because each successful recombination meant one fewer free electron to scatter photons, and fewer scattered photons meant radiation pressure decreased, making further recombination easier. The completion of recombination had 2 immediate and profound effects on the universe. First, with electrons now bound into atoms, photons lost their primary scattering target. Thomson's scattering off free electrons is extraordinarily efficient, but scattering off neutral atoms is much, much weaker. The mean free path of photons, the average distance they could travel before scattering, increased from a few meters to essentially infinite. The universe became transparent. Light could suddenly travel freely across cosmic distances without constantly scattering. This marks the surface of last scattering, the farthest back in time we can see using photons. Any light emitted before recombination has been scattered so many times that it carries no information about where it originally came from. But light emitted at or after recombination travels straight to us, carrying information across billions of light-years of space and billions of years of time. When we observe the cosmic microwave background, we are seeing photons that last scattered off electrons during recombination, about 380,000 years after the Big Bang. Second, recombination released photons in a specific way. As electrons cascaded down to lower energy levels in hydrogen and helium atoms, they emitted photons with specific wavelengths corresponding to atomic transitions. The universe glowed with the light of recombination, a soft glow in what would have been visible and ultraviolet wavelengths at the time. These photons have been redshifted dramatically over the past 13.8 billion years as the universe expanded. Their wavelengths have been stretched by a factor of about 1/100. What was once visible or ultraviolet light is now microwave radiation, forming the cosmic microwave background we detect today at a temperature of 2.7 degrees Kelvin. The cosmic microwave background is one of the most important observations in all of astronomy. It provides a snapshot of the universe at the moment of recombination, showing tiny temperature variations that correspond to density variations in the matter distribution. These variations, imprinted by quantum fluctuations during inflation, served as the seeds for all structure formation. Denser regions had slightly more gravitational pull. Less dense regions had slightly less. Over hundreds of millions of years, gravity amplified these differences, pulling matter from underdense regions into overdense ones, eventually forming the first stars and galaxies. But immediately after recombination, none of that had happened yet. The universe had atoms for the first time. Neutral hydrogen atoms filled space with helium atoms mixed in at about 1 helium for every 12 hydrogen. These atoms had very little kinetic energy relative to today. The temperature of 3000 degrees sounds hot, but it corresponds to atoms moving at only a few kilometers per second. They were not bound into molecules. Molecules require lower temperatures and often require heavier elements to form stable configurations. The universe was a diffuse cooling gas of the simplest atoms, hydrogen and helium, spreading out as space expanded. No stars existed yet, no galaxies, no structure beyond the slight density variations imprinted during inflation. The universe entered a period cosmologists call the Dark Ages, lasting from recombination around 380,000 years after the Big Bang until the first stars formed somewhere between 100 and 300 million years later. During the Dark Ages, the universe was literally dark. The cosmic microwave background photons had redshifted out of visible wavelengths into infrared and eventually microwave. No other light sources existed. Hydrogen atoms occasionally emitted faint 21 centimeter radio waves from spin-flip transitions, but otherwise the universe was silent and lightless. Gravity worked slowly during the Dark Ages, pulling matter together. Denser regions attracted more matter, becoming denser still. Dark matter, which does not interact with light, and therefore was unaffected by radiation pressure even before recombination, had a head start on clumping. Dark matter halos formed first, creating gravitational wells that attracted ordinary matter. Hydrogen and helium gas flowed into these dark matter halos, concentrating in the deepest gravitational valleys. As gas accumulated, its density increased. Pressure increased. Temperature began rising again in the densest concentrations. Eventually, in the cores of the first dark matter halos, conditions became extreme enough to ignite nuclear fusion. Temperatures reached millions of degrees. Hydrogen nuclei collided with enough energy to overcome their electrical repulsion and fuse together. The first stars were born. These stars ended the Dark Ages and began the era of ionization, flooding the universe with ultraviolet light that ionized neutral hydrogen once again, though in a different configuration than before recombination. The cosmic dawn had arrived, but these first stars were made entirely of primordial hydrogen and helium. No carbon existed in their atmospheres, no oxygen, no iron. The universe had successfully created atoms, but it had created only the simplest atoms. Everything more complex, every element that makes modern chemistry possible, every element essential for life, had yet to be forged. That forging would require stars, not just the first generation, but multiple generations, each building on the ashes of those that came before. To understand how the full periodic table came to exist, we must turn to the nuclear furnaces inside stars and the catastrophic explosions that mark their deaths. The first stars that formed in the early universe were unlike any stars we see today, composed entirely of primordial hydrogen and helium, with only traces of lithium. These population 3 stars, as they are called, were massive and short-lived. Many were hundreds of times more massive than our Sun, burning through their nuclear fuel at a ferocious rate and dying in spectacular explosions after only a few million years. But in their brief lives, they accomplished something remarkable. They created the first heavy elements. Stars are fusion reactors, powered by converting lighter elements into heavier ones through nuclear reactions. The energy released in these reactions provides the outward pressure that balances the inward pull of gravity, allowing a star to maintain stable equilibrium for millions or billions of years. But fusion is not primarily about energy production. It is about nucleosynthesis, the creation of new atomic nuclei. Every star is a factory, taking simple ingredients and transforming them into more complex products. The periodic table as we know it was built inside stars. The process begins with hydrogen fusion, the reaction that powers the Sun and most stars for the majority of their lives. In the cores of stars where temperatures reach 15 million degrees Kelvin and pressures are immense, protons collide with tremendous force. Normally, protons repel each other due to their positive electrical charges, but at these high energies, quantum tunneling allows protons to occasionally overcome this repulsion and get close enough for the strong nuclear force to bind them together. 2 protons fuse to form deuterium, with one proton converting into a neutron through weak nuclear interaction, releasing a positron and a neutrino. This is the slowest step in the process, acting as a bottleneck that regulates how fast stars can burn their hydrogen. The deuterium nucleus then fuses with another proton to form helium-3. Finally, 2 helium-3 nuclei collide and fuse, forming helium-4 and releasing 2 protons. This sequence, called the proton-proton chain, is how the Sun converts hydrogen to helium. More massive stars use a different pathway called the CNO cycle, short for carbon-nitrogen-oxygen cycle. In this process, carbon acts as a catalyst. A carbon-12 nucleus captures a proton to become nitrogen-13. The nitrogen decays back to carbon-13, which captures another proton to become nitrogen-14. More proton captures and decays eventually return to carbon-12, but the net effect is still converting 4 protons into one helium-4 nucleus. The CNO cycle is more efficient at higher temperatures, dominating in stars more massive than about 1.3 times the Sun's mass. Either way, the result is the same. Hydrogen converts to helium in the star's core. This process can continue for a very long time because hydrogen is abundant, and because the fusion of hydrogen to helium releases substantial energy per reaction. Our Sun has been fusing hydrogen for about 4.6 billion years, and will continue for another 5 billion years before exhausting the hydrogen in its core. But eventually, every star runs out of core hydrogen. When this happens, the star's core can no longer generate the thermal pressure needed to balance gravity. The core contracts, heating up from gravitational compression. The rising temperature ignites hydrogen fusion in a shell around the helium-filled core. Meanwhile, the outer layers of the star expand dramatically, cooling as they expand. The star becomes a red giant, vastly larger than its previous size, but the real drama occurs in the core. For stars with enough mass, the core eventually reaches 100 million degrees Kelvin. At this temperature, helium fusion becomes possible. 3 helium-4 nuclei can fuse together to form carbon-12 through the triple alpha process. This process is called triple alpha because helium-4 nuclei are also called alpha particles. The reaction proceeds in 2 steps. First, 2 helium-4 nuclei fuse briefly to form beryllium-8. Beryllium-8 is extremely unstable, typically decaying back to 2 helium-4 nuclei in about 10 to the negative 16 seconds. But occasionally, before it decays, a third helium-4 nucleus collides with the beryllium-8, forming carbon-12 in an excited state. The carbon-12 then settles to its ground state by emitting a gamma ray. This process seems impossibly unlikely. The probability of 3 nuclei colliding at exactly the right moment should be vanishingly small. Yet it happens constantly in the cores of red giant stars. The reason is a phenomenon called resonance. Carbon-12 has an energy level, discovered theoretically by Fred Hoyle in 1954 and confirmed experimentally shortly after, that precisely matches the combined energy of beryllium-8 and helium-4. This resonance dramatically increases the reaction rate, allowing triple alpha fusion to proceed at a reasonable pace, despite the unfavourable statistics. The formation of carbon through the triple alpha process represents a critical moment in cosmic history. Carbon is the foundation of organic chemistry and life as we know it. Without this resonance, carbon would be extraordinarily rare, possibly too rare to form planets with substantial carbon content, or to enable carbon-based biology. The fact that this resonance exists has been cited as an example of the anthropic principle, the idea that the universe's physical laws appear fine-tuned to allow for the existence of observers. Whether this is coincidence, necessity, or selection effect remains debated, but the consequence is clear. The universe makes carbon efficiently. Once helium fusion begins, the star has entered a new phase of its life. Helium converts to carbon in the core, while hydrogen continues fusing to helium in a surrounding shell. Some carbon nuclei capture additional helium-4 nuclei, forming oxygen-16. The relative abundance of carbon and oxygen produced depends on the balance between these two reactions, with most stars ending up with comparable amounts of carbon and oxygen in their cores by the time helium is exhausted. For stars similar to or smaller than the Sun, this is essentially the end of fusion. The core becomes a dense ball of carbon and oxygen, supported against gravity by electron degeneracy pressure rather than thermal pressure. The outer layers of the star drift away as a planetary nebula, leaving behind a white dwarf. These stars contribute their carbon and oxygen to the interstellar medium through gentle mass loss, enriching the gas that will form future generations of stars and planets. But more massive stars, those above about 8 solar masses, have enough gravitational pressure to compress and heat their cores beyond 100 million degrees. When carbon and oxygen fill the core and helium fusion ends, the core contracts again, temperature rises. At 600 million degrees, carbon fusion ignites. Carbon nuclei fuse to form neon-20 and magnesium-24. At even higher temperatures approaching 1 billion degrees, Neon fusion produces oxygen and magnesium. Then oxygen fusion creates silicon, sulfur, phosphorus, and other elements around atomic number 14 to 16. Finally, at temperatures exceeding 3 billion degrees, silicon fusion begins. This is not a simple fusion of silicon nuclei, but a complex network of reactions where silicon nuclei are broken down and rebuilt into heavier elements through a series of photodisintegration and fusion reactions. The end products cluster around iron 56 and nickel 56. These nuclei have the highest binding energy per nucleon of any elements. They are the most stable configurations of protons and neutrons possible. This stability creates a critical barrier. Fusing nuclei lighter than iron releases energy because the products are more tightly bound than the reactants. But fusing iron nuclei requires energy input rather than releasing it. You cannot power a star by fusing iron. When a massive star's core becomes dominated by iron and nickel, fusion can proceed no further. The stellar furnace shuts down. The core can no longer generate thermal pressure to support itself against gravity. Collapse is inevitable. This collapse happens catastrophically. The iron core, typically about 1.4 solar masses of material compressed to the density of an atomic nucleus, collapses in less than a second. As it collapses, electrons are forced into protons, forming neutrons and neutrinos. The core becomes a neutron star, or if the star is massive enough, a black hole. But the outer layers of the star, still falling inward at significant fractions of the speed of light, rebound off the incompressible core. A shock wave propagates outward, blasting through the star's outer layers and ejecting them into space at tens of thousands of kilometers per second. This is a supernova, specifically a core collapse or type 2 supernova. In a few seconds, a supernova releases more energy than the Sun will emit in its entire 10 billion year lifetime. The explosion is so bright it can temporarily outshine the entire galaxy containing the supernova. But for our purposes, the importance of supernovae lies not in their light, but in their nuclear alchemy. In the extreme conditions of a supernova explosion, elements heavier than iron can finally form. Throughout a massive star's life, from hydrogen fusion to silicon fusion, nuclear reactions built progressively heavier elements. But this process stopped at iron. The binding energy curve, which measures how tightly bound atomic nuclei are, peaks at iron 56. Creating elements lighter than iron through fusion releases energy because the products are more stable, more tightly bound than the reactants. The mass of the products is slightly less than the mass of the inputs, and that missing mass converts to energy according to Einstein's famous equation E equals mc squared. This energy release is what powers stars and allows them to shine for millions or billions of years. But creating elements heavier than iron through fusion requires energy input rather than releasing it. Iron 56 sits at the peak of the binding energy curve. Fusing iron nuclei together produces less stable products, meaning you have to put energy in to force the reaction. Stars cannot afford this energy cost. They need fusion to provide energy, not consume it. Fusion is their power source, the thermal pressure that holds them up against gravitational collapse. A star that starts consuming energy to create heavy elements rather than releasing energy would quickly find itself in catastrophic trouble. So during normal stellar evolution, elements heavier than iron simply do not form in significant quantities through fusion processes. This presents a profound puzzle when we look around the universe. The Earth beneath our feet contains substantial amounts of elements far heavier than iron. Gold sits at atomic number 79, platinum at 78, lead at 82, uranium at 92. These elements exist in measurable, significant quantities throughout the Earth's crust and in asteroids and meteorites. When we analyze the light from distant stars and galaxies, we see spectral lines corresponding to heavy elements there too. The universe is full of elements that normal stellar fusion cannot create. If stars cannot make them through their regular fusion processes, where did they come from? The answer lies in events far more violent than ordinary stellar fusion. They came from supernovae and neutron star mergers, catastrophic events where conditions briefly become extreme enough to overcome the energy barrier of creating heavy elements. These are not gentle processes. They are some of the most violent events nature can produce, releasing more energy in seconds than the Sun will emit in its entire 10 billion year lifetime. When a massive star's iron core collapses, the sequence of events unfolds with terrifying speed. The core, supported for a brief time by electron degeneracy pressure, reaches a mass limit called the Chandrasekhar limit, about 1.4 solar masses. Beyond this mass, electron degeneracy pressure cannot support the core against gravity. The core becomes unstable. What happens next occurs faster than human reaction time, faster than nerve signals travel, faster than you can blink. The core implodes. Material falls inward at speeds approaching 25% the speed of the light. In less than a second, a region the size of the Earth compresses to a sphere only 20 kilometers across. The density becomes incomprehensible, approaching the density of an atomic nucleus but scaled up to stellar mass. As the core collapses, electrons are forced into protons through inverse beta decay, converting them to neutrons and releasing neutrinos. The core becomes a neutron star, an object so dense that a teaspoon of its material would weigh as much as Mount Everest. The outer layers of the star, still falling inward at tremendous speed, suddenly encounter this incompressible core. They cannot continue falling inward because the neutron degeneracy pressure of the neutron star resists further compression. The infalling material rebounds like a rubber ball bouncing off a concrete floor, but on a stellar scale. A powerful shockwave forms and propagates outward through the star's outer layers. This shockwave blasts through thousands of kilometers of stellar material in seconds, heating it to billions of degrees and accelerating it outward at thousands of kilometers per second. This is a supernova, specifically a core collapse or type 2 supernova. The explosion is extraordinarily luminous. For a few weeks, a single supernova can outshine the entire galaxy containing it. From Earth, we've observed supernovae in distant galaxies that became visible to the naked eye despite being millions of light-years away. In 1987, a supernova occurred in the Large Magellanic Cloud, a small satellite galaxy about 160,000 light-years from Earth. Called SN 1987A, it became the first nearby supernova in the modern era of astronomy, and provided unprecedented data about these explosions. The explosion releases approximately 10 to the 53 ergs of energy, which is 10 to the 46 joules, or about 100 times the energy the Sun will emit in its entire 10 billion year lifetime, released in the span of seconds. Most of this energy, about 99%, escapes as neutrinos. These ghostly particles interact so weakly with matter that they stream out of the collapsing core unimpeded, carrying away the gravitational potential energy released by the collapse. The remaining 1% of the energy goes into the kinetic energy of the ejected material and the light we observe. But for our purposes, the importance of supernovae lies not in their light or their neutrinos, but in their nuclear alchemy. In the extreme conditions of a supernova explosion, elements heavier than iron can finally form in abundance. The mechanism involves neutrons, which are produced copiously during the core collapse and explosion. As electrons merge with protons to form the neutron star core, vast numbers of free neutrons are created. Many of these neutrons escape into the exploding stellar material. Additionally, during the explosion itself, nuclear reactions produce more neutrons. The result is an environment extraordinarily rich in free neutrons. These free neutrons, no longer bound inside atomic nuclei, become the raw material for building heavy elements through a process called neutron capture. The mechanism is elegantly simple in principle, though complex in detail. A heavy nucleus, perhaps iron 56 or nickel 58, sits in the neutron-rich environment of the supernova's expanding debris. A free neutron approaches and collides with it. Unlike protons, which carry positive electrical charge and experience strong electrostatic repulsion from the positively charged nucleus, neutrons have no electrical charge. They feel no electrostatic barrier. They can slip into nuclei relatively easily if they have the right energy and trajectory. The nucleus absorbs the neutron, becoming a heavier isotope of the same element. Iron 56 plus a neutron becomes iron 57, for example. If this new isotope is stable, nothing further happens immediately. The nucleus sits there, one neutron heavier than before. But many neutron-rich isotopes are unstable. They undergo beta decay, a process where a neutron inside the nucleus converts into a proton, emitting an electron and an antineutrino. This increases the atomic number by 1, transforming the element into the next element in the periodic table. This process can repeat. Another neutron is captured. If the resulting isotope is unstable, another beta decay occurs, creating another element. Step by step, nucleus by nucleus, neutron capture followed by beta decay climbs the periodic table. Given enough neutrons, enough time, and the right conditions, even the heaviest naturally occurring elements like uranium-238 and thorium-232 can form through this mechanism. But the details depend critically on how fast neutrons are captured relative to how fast unstable nuclei decay. This timing determines which path through the chart of Nucleides the process follows, and different paths produce different elements and isotopes. Physicists distinguish two main regimes based on this timing. The slow process, called the S process, occurs in certain types of stars, particularly in asymptotic giant branch stars during their late evolutionary phases. In these environments, neutron captures happen slowly enough that unstable isotopes have time to beta decay before capturing another neutron. Imagine nuclei sitting in a neutron environment where neutrons arrive occasionally, perhaps one every few years. A nucleus captures a neutron and becomes a heavier isotope. If that isotope is unstable, it beta decays, perhaps over days or months or years before another neutron arrives. This means the nucleus has time to beta decay back towards stability before adding another neutron. This process follows a path through the chart of Nucleides that stays close to the valley of stability, the region where nuclei have balanced numbers of protons and neutrons and are therefore stable or long-lived. The S process can create many elements heavier than iron, particularly elements like barium, strontium, and others with atomic numbers up to about bismuth-209. But it cannot reach the heaviest elements because the path it follows eventually encounters nuclei with such short half-lives that they decay before capturing another neutron, creating a bottleneck. Additionally, some heavy elements require more neutron-rich isotopes than the S process can produce. These elements must form through a different mechanism. The rapid process, called the R process, occurs in environments with such extraordinarily high neutron densities that many neutrons are captured in rapid succession before any beta decays can occur. Imagine a nucleus in an environment so saturated with neutrons that it captures one, then another in quick succession. Faster than it can decay, the nucleus becomes extraordinarily neutron-rich, containing far more neutrons than it can stably hold, far from the valley of stability. Eventually, the neutron bombardment stops, perhaps because the environment cools or expands or the neutron supply is exhausted. Now the nucleus finds itself extremely unstable, loaded with excess neutrons. It undergoes not just one beta decay, but a cascade of them, a chain reaction of neutron to proton conversions. Each beta decay increases the atomic number by 1, moving to the next element in the periodic table. The cascade continues until the nucleus reaches stability, or at least a long-lived configuration. This R process can create the heaviest elements that exist in nature, including gold, platinum, uranium, and thorium. It can produce neutron-rich isotopes that the S process cannot reach. Many elements we observe in nature are created primarily or exclusively by the R process. The relative abundances of different isotopes carry signatures of whether they formed through the S process or R process, allowing astronomers to identify which process dominated in different environments. For decades, supernovae were thought to be the primary, perhaps the exclusive site of R process nucleosynthesis. The neutron-rich material ejected in a core-collapse supernova seemed like the perfect environment. Theoretical models in the 1950s through 1990s suggested that R process elements would form in the neutrino-driven winds of material flowing off the nascent neutron star immediately after core collapse. As neutrinos stream out of the newly formed neutron star, they deposit energy in the overlying material, driving winds that carry matter away at high velocities. These winds are neutron-rich and seemed ideal for the R process. However, as computer simulations became more sophisticated and detailed in the 2000s and 2010s, problems with this scenario emerged. The conditions in supernova ejecta might not be quite right to produce the observed abundances of R process elements across the full range from lighter to heavier species. The neutron densities achieved might be too low, or the entropies too high, or the timescales wrong. The simulations could produce summer process material, but not enough to account for what we observe in the universe, and not with the right abundance patterns. Then, on August 17, 2017, a different source of R process elements was detected directly for the first time, and it revolutionized our understanding. The LIGO gravitational wave detectors in the United States and the Virgo detector in Italy observed ripples in spacetime consistent with the merger of two neutron stars. This event, designated GW17 occurred in a galaxy about 130 million light-years away. Within seconds of the gravitational wave detection, telescopes around the world swung into action, scanning the region of sky where the merger occurred. They found it. A new point of light appeared in the galaxy NGC 4993, exactly where the gravitational wave signal originated. This was not a typical supernova. Its light curve, the way its brightness changed over time, was different. Its spectrum, the rainbow of wavelengths it emitted, showed unusual features. Within hours, astronomers realized they were witnessing something predicted but never before observed: a kilonova, an optical and infrared transient powered by the radioactive decay of freshly synthesized heavy elements. The light curves and spectra matched predictions for R-process nucleosynthesis almost perfectly. The merger had ejected substantial quantities of neutron-rich material at velocities of 10 to 30% the speed of light. This material, extraordinarily rich in neutrons because it came from the surfaces of neutron stars where matter exists in exotic states, underwent rapid neutron capture. Within seconds of the merger, R-process nucleosynthesis created heavy elements. These newly formed heavy elements, many of them radioactive, decayed over hours and days, releasing energy that heated the expanding cloud of debris and caused it to glow. The spectrum showed absorption features consistent with elements like lanthanides, a series of rare earth elements that are difficult to produce through any process except the R process. The estimated mass of heavy elements produced was staggering, somewhere between 1/100th and 1/10th of a solar mass. That may sound small, but it represents an enormous quantity of gold, platinum, uranium, and other heavy elements, all created in a single event lasting seconds. Neutron star mergers are now recognized as a major, perhaps the dominant source of R-process elements in the universe. When two neutron stars spiral together and collide, tidal forces tear material from their surfaces before they merge. This material, flung out at relativistic speeds, is extraordinarily neutron-rich, consisting almost entirely of neutrons with a small fraction of protons and electrons, perfect conditions for the R process. The ejected material, perhaps a few percent of a solar mass in total, undergoes rapid neutron capture, building up heavy nuclei before decaying into the stable heavy elements we observe. Estimates suggest that a single neutron star merger can produce several percent of a solar mass worth of heavy elements, with the equivalent of multiple Earth masses of pure gold. Given the frequency of neutron star mergers in galaxies, estimated at a few per million years per galaxy, and the billions of years of cosmic history neutron star mergers can account for much or most of the R-process material we observe in the universe today. Each merger is a cosmic gold mine, quite literally, seeding the interstellar medium with precious metals and other heavy elements. Supernovae may still contribute to R-process nucleosynthesis through other mechanisms not yet fully understood, and the relative importance of each source remains an active area of research. Different galaxies might have different histories depending on their rates of supernova and neutron star mergers. But the 2017 kilonova observation proved beyond doubt that neutron star mergers are prolific creators of the heaviest elements. There are other exotic processes that contribute trace amounts of certain elements. Cosmic ray spallation, where high-energy particles smash into nuclei and fragment them into smaller pieces, creates some of the lightest elements like lithium, beryllium, and boron that are otherwise extremely rare. These elements are not efficiently produced in either Big Bang nucleosynthesis or stellar fusion, but cosmic rays can create them by breaking apart heavier nuclei like carbon, nitrogen, and oxygen. Neutrino-induced reactions in supernovae contribute to specific rare isotopes. The intense neutrino flux from a core-collapse supernova can induce nuclear reactions in the star's outer layers, creating unusual isotopes that would not form through other processes. Certain types of stellar explosions, like novae on white dwarf surfaces in binary systems, create their own unique abundance patterns, particularly of elements like nitrogen, oxygen, and sodium. Each astrophysical site has its signature, and by studying the abundances of elements and isotopes in stars, the interstellar medium, and meteorites, astronomers can piece together which processes operated where and when. But the big picture is clear and elegant. Hydrogen and helium, the two lightest and most abundant elements, came from the Big Bang in the first few minutes of cosmic history. Helium-4 makes up about 25% of ordinary matter by mass, hydrogen about 75%, traces of deuterium and helium-3 and lithium-7 making up the rest. This primordial composition has persisted across cosmic time, modified but not erased by later processes. Carbon, nitrogen, oxygen, and elements up to iron came from stellar fusion in the cores of stars over billions of years. Each generation of stars created these elements from hydrogen and helium, then scattered them into space either gently through stellar winds or explosively through supernovae. The interstellar medium gradually became enriched with heavy elements. Elements heavier than iron came primarily from neutron capture in two main sites: the S process in asymptotic giant branch stars and the R process in supernovae and, especially, neutron star mergers. The periodic table is a cosmic archaeological record, each element telling the story of where and how it formed, carrying the signature of the nuclear processes and astrophysical environments that created it. The calcium in your bones was forged in a massive star's oxygen-burning shell that exploded billions of years ago. The iron in your blood was created in the final moments of a star's life just before it went supernova, when silicon fusion in the star's core built up an iron core that could fuse no further. The iodine in your thyroid, essential for regulating metabolism, came from the R process, likely in a neutron star merger somewhere in our galaxy's history. And if you wear gold jewellery, those gold atoms almost certainly came from a neutron star merger. Two incredibly dense stellar remnants, each about 1.4 times the mass of the Sun but compressed into a sphere only 20 kilometers across, about the size of a city, spiraled together over millions or billions of years, their orbits decaying as they radiated gravitational waves. In the final moments before collision, tidal forces more extreme than anything we can easily imagine ripped material from the neutron star's surfaces. This material underwent the most rapid neutron capture possible. Within seconds, nuclei were built up from iron to uranium and beyond, creating all the heaviest elements in nature. The collision ejected these newly formed elements into space in glowing clouds that expanded at significant fractions of the speed of light. The material cooled and spread through the interstellar medium over millions of years. Eventually it became incorporated into the molecular cloud that collapsed to form our Sun and solar system. Some of it ended up on Earth, where humans eventually dug it out of the ground, refined it, and fashioned it into jewellery, completely unaware of the violent cosmic origins of this metal. This cosmic alchemy has been ongoing for more than 13 billion years, ever since the first stars formed a few 100 million years after the Big Bang. The first stars, called population 3 stars, were made of only hydrogen and helium from the Big Bang. They contained no heavy elements at all, no metals in astronomers' terminology where anything heavier than helium counts as a metal. These stars lived fast and died young, burning through their nuclear fuel in just a few million years before exploding as supernovae. Their explosions enriched the surrounding gas with the first heavy elements: carbon, oxygen, silicon, magnesium, iron, and traces of heavier elements from whatever R process occurred in their deaths. That enriched gas collapsed to form a second generation of stars, now containing trace amounts of heavy elements, perhaps 1/10,000th the concentration of heavy elements in the Sun. These second-generation stars, called population 2 stars, created more heavy elements through their fusion processes, enriched the interstellar medium further through their stellar winds and eventual supernova, and the cycle continued. Each generation increased the metallicity, the fraction of heavy elements. Our Sun, a population 1 star formed about 4.6 billion years ago, contains about 2% heavy elements by mass. That might sound small, but it represents enrichment from countless previous generations of stars over 9 billion years of galactic chemical evolution. That 2% of heavy elements allowed solid planets to form in our solar system. Rocky worlds like Earth simply could not exist in a universe with only hydrogen and helium. Planets require silicon for rocks, iron for cores, oxygen to combine with silicon and iron, carbon for organic chemistry. Life requires chemistry, and chemistry requires diverse elements. The carbon-based life on Earth needs carbon, obviously, but also hydrogen, oxygen, nitrogen, phosphorus, sulfur, and trace amounts of many other elements like iron, calcium, potassium, sodium, magnesium, zinc, copper, iodine, selenium. Every one of these elements has a cosmic origin story. Everyone was created in stars or in the Big Bang and scattered through space to eventually be incorporated into the molecular cloud that formed our solar system and ultimately into living organisms. The atoms in your body are older than the sun, older than the Earth, older than anything you can see around you. They were forged in stars that died before our solar system even existed. Some of those atoms, the hydrogen nuclei that make up much of the water in your body, are even older, created in the first few minutes after the Big Bang when the universe was an expanding fireball. The oxygen you breathe with every breath came from massive stars that fused helium into carbon and carbon into oxygen over millions of years, then exploded and scattered those elements into space. The nitrogen in your DNA, essential for encoding genetic information, formed through the CNO cycle in stellar cores, created when carbon, nitrogen, and oxygen nuclei participated in the complex chain of reactions that power massive stars. The calcium in your bones, providing structural support for your skeleton, was created in the oxygen-burning and silicon-burning phases of massive stars in their final days before going supernova. The phosphorus in ATP molecules that power every cellular process in your body formed in similar environments in the nuclear furnaces of dying stars. The iron in hemoglobin that carries oxygen through your bloodstream was created in the final hours or days before a supernova, when silicon fusion in a massive star's core built up an iron core that could undergo no further fusion. When that core collapsed and the star exploded, the iron was ejected into space, along with silicon, sulfur, calcium, and dozens of other elements. The iodine concentrated in your thyroid gland, essential for producing hormones that regulate metabolism, came from the R process, created when free neutrons bombarded heavy nuclei in environments of extreme neutron density, likely in a neutron star merger somewhere in our galaxy's past. You are literally made of stardust, assembled from atoms created in some of the most violent events the universe can produce. This is not poetry or metaphor. It is physics and chemistry traced back through cosmic history. Every element heavier than lithium in your body came from stars. Every chemical reaction in your body involves atoms that existed for billions of years before Earth formed, that cycled through previous generations of stars and planets, that drifted through interstellar space for millions of years before being incorporated into the molecular cloud that collapsed to form our solar system. We have traced the origin of atoms from the quantum vacuum to the death of stars. The story spans more than 13 billion years and ranges from the smallest scales physics can describe to structures larger than galaxy clusters. But before we conclude, let us pull back and see the complete picture, understanding how each stage built upon what came before and led to the rich complexity we observe today. This is not just a chronological sequence of events, but a coherent narrative of increasing organization, from simple to complex, from uniform to diverse, from sterile to potentially fertile. In the beginning, if we can call it that, there was the quantum vacuum. Not true nothingness, but a seething foam of virtual particles popping in and out of existence according to the uncertainty principle. In this state, the universe existed in a false vacuum, a temporary high-energy condition that seems stable but contains enormous potential energy. Quantum fluctuations in the inflaton field, whatever that field truly is, drove cosmic inflation. The universe expanded exponentially, doubling in size again and again in unimaginably brief intervals. A region smaller than a proton ballooned to larger than the observable universe in a tiny fraction of a second. These same quantum fluctuations, stretched to cosmic scales by the runaway expansion, became the seeds of all structure. What started as quantum uncertainty on scales smaller than any particle ended up as variations in density spanning billions of light years. The universe, which might have been perfectly uniform, gained texture and variation because quantum mechanics ensures that perfect uniformity cannot exist even in principle. When inflation ended, the false vacuum decayed and released its energy as particles. The universe filled with a hot, dense plasma, temperatures measured in the quadrillions or quintillions of degrees, levels we can barely approach even in our most powerful accelerators. At these energies, quarks and gluons existed freely as a quark-gluon plasma. The strong force, despite its name, was weak enough at these extreme conditions that quarks could not bind together. They moved independently, colliding constantly, interacting intensely, but never forming stable composite particles. As the universe expanded, it cooled. Temperature and density dropped continuously, inexorably. When temperatures fell below about 2 trillion degrees, perhaps a few microseconds after the beginning, quarks confined into hadrons. The strong force became dominant. Gluons successfully bound quarks together into protons and neutrons. This transition, called hadronization, marked the end of the quark epoch and the beginning of the hadron epoch. But crucially, a tiny asymmetry existed. For every billion matter-antimatter pairs that annihilated into pure energy, one matter particle survived. Every atom that exists today emerged from that 1 in a billion excess. About 1 second after the Big Bang, the universe had cooled to about 10 billion degrees. Neutrinos decoupled from ordinary matter, streaming freely through space and contributing to a cosmic neutrino background we have never directly detected but know must exist. The ratio of neutrons to protons froze out at about 1 neutron for every 6 protons, though this ratio would change slightly as free neutrons decayed over the next few minutes. At 3 minutes, with temperatures around 1 billion degrees, Big Bang nucleosynthesis began. The deuterium bottleneck opened. Protons and neutrons could finally stick together when they collided, forming deuterium nuclei that survived long enough to participate in further reactions. Nuclear fusion proceeded rapidly for the next 15 to 20 minutes, building up helium-4 as the primary product, along with smaller amounts of deuterium, helium-3, and lithium-7. But the mass gaps at 5 and 8 nucleons prevented the formation of anything heavier than lithium. By 20 minutes after the Big Bang, the universe had cooled to about 300 million degrees, too cool for further nuclear reactions. The primordial abundance was set: 75% hydrogen, 25% helium-4, traces of deuterium and lithium-7. But these were nuclei, not atoms. For the next 380,000 years, the universe remained a hot plasma of nuclei and electrons, completely opaque to light due to constant photon scattering off free electrons. Thomson's scattering was so efficient that light could not travel more than a few meters without hitting an electron and changing direction. The universe was filled with light, but that light was trapped, constantly scattered, unable to stream freely across space. This was the photon epoch, when radiation dominated the energy content of the cosmos, and matter was merely a passenger buffeted by intense radiation. As the universe expanded, it cooled. The photons' energies decreased, their ability to ionize atoms weakened. Around 47,000 years after the Big Bang, the energy density of matter surpassed that of radiation for the first time. The universe transitioned from radiation-dominated to matter-dominated. Gravity could finally begin pulling matter together without radiation pressure fighting against it. But atoms still could not form. The temperature remained too high. The universe continued expanding. The cosmic clock ticked past 100,000 years, 200,000 years, 300,000 years. Each passing millennium, temperatures dropped a little further. Finally, at about 380,000 years, when temperatures had fallen to roughly 3,000 degrees Kelvin, recombination occurred. Electrons could finally bind permanently to nuclei. The process unfolded over tens of thousands of years as electrons cascaded down through atomic energy levels, emitting photons as they settled into stable orbits. 90% of electrons bound into neutral atoms. With electrons now bound, photons lost their primary scattering target. The mean free path of light increased from meters to effectively infinite. The universe became transparent for the first time. Light could travel freely across cosmic distances. The photons released during recombination, having scattered for the last time off free electrons, began journeys that would last billions of years. These photons, redshifted by cosmic expansion over the intervening eons, reach us today as the cosmic microwave background, cooled from 3,000 degrees to 2.7 degrees Kelvin. The universe now contained atoms, but only the simplest ones. Hydrogen atoms with 1 proton and 1 electron. Helium atoms with 2 protons, 2 neutrons and 2 electrons. Traces of lithium atoms with 3 protons. No carbon, no oxygen, no silicon, no iron. No elements that could form complex chemistry. No materials that could build rocky planets. The universe entered the Dark Ages, literally dark because the cosmic microwave background had redshifted out of visible wavelengths and no other light sources existed yet. For hundreds of millions of years, the universe was lightless. Gravity worked slowly, pulling matter together. Denser regions attracted more matter, becoming denser still. Dark matter, unaffected by radiation even before recombination, had a head start and formed the scaffolding. Dark matter halos collapsed first, creating gravitational wells into which ordinary matter flowed. Hydrogen and helium gas concentrated in these dark matter halos. As gas accumulated, density and temperature rose. Eventually, in the cores of the first dark matter halos, between 100 and 300 million years after the Big Bang, conditions became extreme enough to ignite nuclear fusion. The first stars were born, massive and short-lived, burning through their hydrogen in just a few million years. These population 3 stars, made entirely of primordial hydrogen and helium, were the first light in a dark universe. They ended the cosmic dark ages and began reionization, flooding space with ultraviolet radiation that ionized neutral hydrogen once again. But more importantly for our story, these first stars began stellar nucleosynthesis. In their cores, hydrogen fused to helium through the proton-proton chain, or CNO cycle. In the most massive stars, when hydrogen was exhausted, helium fused to carbon through the triple alpha process. Carbon fused with helium to make oxygen. Successive burning stages created neon, magnesium, silicon, sulfur. Finally, silicon fusion created iron. When these massive first-generation stars exploded as supernovae, they scattered these newly created elements into the surrounding intergalactic medium. The enriched gas collapsed to form second-generation stars, population 2 stars, now containing trace amounts of heavy elements. These stars continued the process, fusing light elements into heavy ones, enriching the interstellar medium further through stellar winds and supernovae. Each generation increased the metallicity of the gas. After billions of years of this chemical evolution, the gas that formed our Sun contained about 2% heavy elements by mass. This 2% made all the difference. It allowed solid materials to condense in the protoplanetary disk around the young Sun. Rocky planets formed through accretion of dust and small bodies. Earth accumulated enough mass to differentiate into core, mantle, and crust. Oceans formed from water delivered by comets and asteroids. An atmosphere developed, and in those oceans, somewhere around 3.8 to 4 billion years ago, chemistry became complex enough to support self-replication. Life emerged. Every step in this narrative was necessary. Remove any one, and the chain breaks. Without inflation, the universe might have remained tiny and collapsed back on itself almost immediately. Or it might have been so inhomogeneous that no structure could form. Without the matter-antimatter asymmetry, everything would have annihilated, leaving only radiation. Without Big Bang nucleosynthesis, the universe would contain only hydrogen, with no helium to fuel the triple alpha process in stars. Without recombination, the universe would remain opaque, and gravity's ability to form structure would be severely hindered. Without stars, no heavy elements would form beyond lithium. Without supernovae and neutron star mergers, elements heavier than iron would not exist. Without rocky planets, chemistry would be limited to gas phase reactions in stellar atmospheres and interstellar clouds. Without the right mix of elements, carbon-based chemistry might not be possible. Every stage built on what came before, creating the conditions for what came next, in a cosmic chain of causation stretching from quantum fluctuations to conscious observers. The timeline of atom formation can be summarized simply, though the processes involved are anything but simple. Hydrogen nuclei, just single protons, formed within the first second after the Big Bang when quarks confined into hadrons. Helium nuclei formed in the first 20 minutes through Big Bang nucleosynthesis. Lithium nuclei formed in tiny quantities during the same era. Elements from carbon to iron formed inside stars over billions of years through successive fusion reactions, with each star contributing its share to the growing inventory of heavy elements in the interstellar medium. Elements heavier than iron formed in supernovae through explosive nucleosynthesis and neutron capture, and in neutron star mergers through the R process. The first atoms, meaning nuclei with bound electrons, formed at recombination 380,000 years after the Big Bang. But these were only hydrogen and helium atoms. Atoms of heavier elements had to wait for stars to create those elements first, then die and scatter them into space, then for new generations of objects to form incorporating these heavy elements. The first carbon atoms, the first oxygen atoms, the first iron atoms, each appeared only after stars had existed long enough to produce them and explode to distribute them. This process took hundreds of millions of years for the lightest heavy elements like carbon and oxygen and billions of years to build up significant quantities of elements across the periodic table. Our solar system, forming 4.6 billion years ago, about 9 billion years after the Big Bang, inherited an inventory of elements created over that entire preceding period. It took roughly 200 million years for the first stars to form after the Big Bang. Perhaps another few hundred million years for the first generation of massive stars to die and enrich their surroundings with heavy elements. Maybe 1 billion years or more before enough heavy elements existed to form rocky planets like Earth. And on Earth, another 4 billion years of evolution from simple chemicals to complex life, capable of asking questions about its own origin, about the atoms it is made from, about the journey from quantum foam to consciousness. The atoms in your body are cosmopolitan travellers with ancient histories. The hydrogen in your water is 13.8 billion years old, created when the universe was minutes old in Big Bang nucleosynthesis. The helium in helium balloons and in the Sun is similarly ancient, mostly primordial, with small contributions from stellar fusion. The carbon, nitrogen and oxygen in your organic molecules are younger but still incredibly old, perhaps anywhere from a few billion to 10 billion years old, created in stars that lived and died during the universe's middle age. The iron in your blood might be 5 billion years old or 15 billion years old. We cannot know the specific history of individual atoms. It formed in a massive star somewhere in the galaxy, perhaps in the star that exploded and contributed to the enriched molecular cloud that eventually collapsed to form our solar system, or perhaps in an earlier generation whose products were recycled through multiple generations of star formation. The calcium in your bones, the phosphorus in your DNA, the sulfur in your proteins, the sodium and potassium that enable nerve impulses, all have similar ancient origins in stellar furnaces and supernova explosions. Some atoms in your body might have cycled through other organisms before you. The carbon atom in a protein in your muscles might have previously been part of a dinosaur, or a fish, or a flower, or a bacterium. It might have spent millions of years locked in limestone rock before erosion and geological processes liberated it. It might have been atmospheric carbon dioxide for a time before being incorporated into a plant through photosynthesis, then eaten by an animal, then decomposed by bacteria, then returned to the atmosphere, and so on through countless cycles. You are a pattern of atoms temporarily organised in a particular configuration. The atoms themselves endure almost unchanging. The pattern changes constantly. Every few years, through metabolic processes of eating, drinking, breathing and excreting, nearly all the atoms in your body are replaced. You eat food, breaking down complex molecules into simple ones, then reassembling them into your own tissues. Old atoms leave, new atoms arrive. The pattern that is you persists even as the material constantly changes, but those atoms will outlast you, will outlast humanity, will outlast the Earth and Sun. After you die, however your atoms return to the environment, they continue cycling through Earth's systems. Some return to the biosphere, taken up by plants or microorganisms. Some enter the ocean, or atmosphere or lithosphere. They continue their journey through the planet's interconnected systems for millions or billions of years. Eventually, perhaps 4 or 5 billion years from now, the Sun will exhaust its hydrogen and expand into a red giant, growing large enough to engulf Earth's orbit. Your atoms, or at least some of them if Earth is not completely vaporized, will be incorporated into the expanding outer layers of the dying Sun. When the Sun finally dies, shedding those outer layers as a planetary nebula and leaving behind a white dwarf core, your atoms will be among those ejected into space. They will drift through the interstellar medium for millions of years, perhaps joining a molecular cloud. That cloud might collapse to form new stars and planets billions of years from now in a galaxy that might not even be the Milky Way anymore, since Andromeda and the Milky Way will have merged by then. Carbon atoms that once formed part of your DNA might end up billions of years hence as part of new life forms on a planet circling a star that has not yet been born, in a galaxy not yet formed from the merger. The cycle continues indefinitely into the future, limited only by whether protons eventually decay, which some theories predict but we have never observed, or by the eventual heat death of the universe when entropy reaches its maximum and all useful energy has been dispersed. This is the ultimate cosmic recycling program, the grand cycle of matter through stars, planets, life and back to space to begin again. Atoms are essentially indestructible through ordinary chemical and physical processes. They can be rearranged endlessly, ionized and recombined. incorporated into different molecules and materials and organisms, but they persist. Only in the most extreme conditions do atoms truly cease to exist as we know them. In the interiors of neutron stars where matter is compressed beyond nuclear density, at the event horizons of black holes where space-time itself becomes infinitely curved, or possibly in the far future if protons decay. The story of how atoms formed from nothing is not just cosmic history. It is intimately personal history. Every breath you take connects you to the Big Bang through the primordial hydrogen and helium created in those first 20 minutes. Every heartbeat connects you to exploding stars through the iron in your hemoglobin. Every thought connects you to dying stars and neutron star mergers through the diverse elements that enable the complex biochemistry of your brain. You're not separate from the universe. You're a way the universe has organized a small fraction of its atoms to be conscious, to think, to wonder about origins. The atoms that wonder about atoms are the same atoms forged in the cosmos billions of years ago. We are, in the most literal and profound sense, the universe contemplating itself. The journey from quantum fluctuations to conscious thought is long and complex, involving physics we only partially understand and processes occurring on scales from the tiniest subatomic distances to the largest cosmic structures. But we can trace that journey. We can understand, at least in outline, how everything emerged from almost nothing, how simplicity gave rise to complexity, how sterile gave birth to fertile. This understanding is one of humanity's greatest intellectual achievements. In just a few centuries, we have progressed from speculation about the nature of matter to detailed knowledge of where every element came from and when it formed. We can look at the periodic table and tell the story of each element. Hydrogen from the Big Bang, helium mostly from the Big Bang, lithium from the Big Bang and cosmic rays, carbon through iron from stellar fusion, beyond iron from neutron capture in extreme environments. Each element is a chapter in the cosmic story, and this story is not complete. We continue discovering new details, refining our understanding. The discovery of neutron star mergers as R-process sites happened only in 2017. Our models of stellar evolution and supernova explosions continue improving as we gain better data from observations and build more sophisticated simulations. We are still working out the details of how the first stars formed and what they were like. We do not yet understand dark matter and dark energy, which together make up 95% of the universe's content but whose nature remains mysterious. Future observations will probe the universe to greater distances and earlier times. The James Webb Space Telescope is designed to see the first galaxies forming in the early universe, pushing our observational horizon back toward the dark ages. Next-generation gravitational wave detectors will observe more neutron star mergers and perhaps other exotic phenomena. Improved particle accelerators might reveal new physics beyond the standard model, helping us understand what happened in the first instance after the Big Bang. But even with gaps in our knowledge, the overall picture is clear and has been confirmed by countless observations across multiple fields of astronomy and physics. The universe began in a hot, dense state. It expanded and cooled. Simple structures formed first, then more complex ones. Atoms emerged from quarks through a sequence of transitions as temperature dropped. The lightest nuclei formed through Big Bang nucleosynthesis, heavier nuclei through stellar fusion, the heaviest through neutron capture in extreme environments. Recombination created the first atoms. Subsequent cosmic evolution created planets, and eventually life. This narrative is supported by evidence ranging from the cosmic microwave background to the abundances of light elements, to the observations of distant supernovae, to the detection of gravitational waves from merging neutron stars. Multiple independent lines of evidence converge on the same story, giving us confidence that we genuinely understand, at least in broad strokes, the origin and evolution of atoms. We have journeyed from quantum fluctuations in the void to the periodic table of elements. We have witnessed the birth of quarks from energy, the formation of protons and neutrons, the fusion of light nuclei in the primordial furnace, the creation of atoms at recombination, and the forging of heavy elements in stellar cores and supernova. The story spans scales from the Planck length to galactic distances, timescales from the Planck time to billions of years. The most remarkable aspect of this story is that we can tell it at all. The atoms in our brains, arranged in complex patterns we call neurons, allow us to understand the processes that created those very atoms. Physics, which began as humans observing falling objects and planetary motions, has developed to the point where we can describe the first microsecond after the Big Bang with mathematical precision. We can recreate quark-gluon plasma in particle accelerators. We can measure the cosmic microwave background to exquisite accuracy. We can detect gravitational waves from neutron star mergers and watch them forge heavy elements in real time. Yet mysteries remain. We do not fully understand what drove inflation or what the inflaton field actually is. We do not know why matter dominated over antimatter, or what mechanism created that crucial asymmetry. The lithium problem suggests our understanding of Big Bang nucleosynthesis may be incomplete. We are still refining our models of stellar evolution and supernova explosions. The relative contributions of different sources to our process elements remain uncertain, and beyond the scope of this story lie even deeper questions. What came before the Big Bang, if that question even makes sense? Is our universe unique, or are there others with different physical laws and different histories? Could atoms form through entirely different processes in other regions of a larger multiverse? These questions remain at the frontier of theoretical physics and cosmology. But for now, we have answered the core question: how did atoms form from nothing? Through quantum fluctuations amplified by inflation, through the cooling and confinement of quarks, through primordial nucleosynthesis in the first minutes, through recombination after hundreds of thousands of years, and through billions of years of stellar alchemy. Every stage was necessary. Remove any one, and atoms as we know them could not exist. The atoms that make up everything you see, everything you touch, everything you are, came from the most violent and energetic events the universe can produce. They came from the Big Bang itself. They came from the cores of massive stars burning at hundreds of millions of degrees. They came from supernova explosions that briefly outshone galaxies. They came from the collision of neutron stars in catastrophic mergers. The peaceful, stable atoms that form mountains and oceans and living cells carry within them the legacy of cosmic violence, and the journey continues. Stars are still forming from molecular clouds enriched by previous generations. Supernovae are still exploding, still scattering heavy elements across the cosmos. Neutron stars are still merging, still creating gold and platinum and uranium. The cosmic enrichment process that began with the first stars billions of years ago continues today. Future generations of stars will form from material even more enriched than what created our Sun. Future planets may have even higher abundances of heavy elements. Future life, if any arises, will be built from atoms forged over an even longer cosmic history. We are privileged to live in an era when we can understand these processes. Earlier civilizations could wonder about the nature of matter but lacked the tools to probe its origins. Future civilizations, billions of years hence when the universe has expanded far more and the cosmic microwave background has redshifted into invisibility, may not be able to discover evidence of the Big Bang at all. We live in a golden age of cosmology, with powerful telescopes and particle accelerators, with space missions and gravitational wave detectors, allowing us to piece together cosmic history from the first fraction of a second to the present day. If you found this journey through the origin of atoms fascinating, show your support by hitting that like button and subscribing to the channel. There are countless more mysteries to explore, from the nature of dark matter and dark energy to the possibility of other universes, from the formation of the first galaxies to the ultimate fate of the cosmos. The atoms may be ancient, but our understanding of them is constantly evolving. Stay curious, keep questioning, and remember that every time you look at the night sky or contemplate the nature of existence, you're engaging in the same process that led from quantum foam to conscious thought. Your atoms asking about atoms, the universe understanding itself. Thank you for joining me on this cosmic journey. Until next time, keep looking up and keep wondering about the magnificent universe we inhabit.